Welcome to the new session. In the last class, we discussed about the linear combinations and linear span of a vector space. Today's class, we start with the linear independence and dependence. So, in the last class, we discussed about the linear combinations. So, we start with the trivial linear combination. What is the trivial linear combinations? So, if V1, V2, Vn are n vectors of a vector space V, then linear combinations we can write in the form of a scalar times of a V1, alpha 1 V1 plus alpha 2 V2 plus so on alpha n Vn. And this is called is a trivial linear combinations only if all the scalars are 0. So, we can say that this linear combination is called is a trivial linear combination if these scalars alpha 1, alpha 2, alpha 1, this should be equal to 0, this should be equal to 0 and so on, each and every scalar should be equal to 0. If otherwise, we can say that this is a linear combination is a non-trivial linear combination. For example, if we take any linear combination for the moment, we take a for example set is V1 R2, we take an R2, we have a two vectors V1 and V2. So, this is a trivial linear combination only in the form of a 0 into V1 plus 0 into V2 in this form, where alpha 1 we can write as a linear combination in the form of alpha 1 V1 plus alpha 2 V2. If this alpha 1 and alpha 2 we take as 0, so this is called is a trivial linear combination. If this vector can be written as 1 into V1 plus 0 into V2 is called is a non-trivial linear combination, or you can say that some 1 into V1 plus 1 into V2 is also is a non-trivial linear combination. So, we can say simply say that linear combinations is only those vectors, we write a linear combination of the vectors of a V1, V2 and whenever all the scalars are is equal to 0, we can say that 0 V1, 0 V2 and so on 0 Vn is called is a trivial linear combination. If any one of them alpha is not equal to 0, we can say that is a non-trivial linear combination, or all the alphas are non-zero is also called is a linear non-trivial linear combination. For example, if we take a, I just say that we can write all the 0 0 0 V1 plus 0 V2 and so on Vn, and this is called is a trivial linear combination. And if we write in the form of 0 V1 0 V2 0 and last one is equal to 1 into Vn, and that means this should be is equal to clearly is a non-zero element. So, we can say that is a non-trivial linear combinations of n vectors. Similarly, we can say that 1 into V1, 2 into V2 up so on n Vn n minus 1, and then we have to just say that up to plus we can add is equal to or leave this is equal to this is should be divide this should be as equal to n is not n Vn, and in this case is also is a this is not a n minus 1, this should be Vn. So, is also is a non-trivial linear combination. Okay, so note that the trivial linear, this is very important, trivial linear combination of any set of vector is always if this is equal to 0. Why this is equal to 0? We can say that we have a 0 V1, we know that the property of a in the vector space is a vector space. So, we know the property of a vector space saying that we have a 0 into V is equal to 0 of a V, and then clearly if you have a 0 of V1, this is equal to 0 additive identity of this. Similarly, 0 of V2 is also the additive identity is giving. So, this is you have a giving the additive identity, this is also giving you have a additive identity, is also giving the additive identity. So, this and all these things form. And now we know that the by the property of a we have to take a additive identity element, so u plus 0 is equal to u, or we have a 0 plus 0 is equal to 0 by the property of a additive identity of vector space. We take a sum of these two is equal to 0 for V and so on like this. So, this means ultimately we have to getting to this. So, this means that is a very important things. We can say that the trivial linear combination of on any set of vectors always be a 0 vector. So, that means this giving you a trivial linear combination of vectors always giving you a 0 vector. This is the this is very important concept, because in this form here we can introduce the concept of a we define the concept of a linearly independence of a vector. So, now before defining the linear independent of a vectors or not, from here is naturally the question is arising, if we have a trivial linear combination, then we have to show that this is clearly is always is equal to the 0 vector. But the question arises whether a non-trivial linear combination of a set of vectors give a 0 vector, because there is a possibility is there. If we take a non-trivial linear combination, and then also is possible we have to give the 0 vector or not. So, answer is affirmative. Why answer is affirmative? We take one example. For example, we write into this form. So, this we can write into this form. We can just say that you have a like into this form. So, we have a this is the vectors we have to write. We have to try to write a linear combination of this. For example, I write it 2 times of a 1 comma 0 comma 0 plus minus 1 times 2 comma 0 comma 0, and then we have again we have a plus 1 times we have a 0 0 1. Now, this is clearly giving you have a 2 0 0 plus you have a minus 2 0 0 and plus 0 0 1, and then the property of this is equal to 2 plus minus 2 plus 0 0 plus 0 plus 0, and then you have a 0 plus sorry, this is equal to you have a we take this is equal to 0. So, this is sorry, this is equal to 0. So, we have to take a 0 element here. So, this is nothing but is equal to you have a 0 plus 0 plus 0, and this is giving you a 0 and 0 and 0. So, this is nothing but is equal to 0. So, that means we can take a 3 elements, and that is a this linear combination is clearly is a non-trivial linear combination, where this is scalar is a non-zero, this is scalar is a non-zero, or we can write into different way also is a 1 into this and then is and similarly into this form is this 1 minus 1 by 2 minus 1 or 1 by 2 we can write into other form also. This, for example, I can write into this 1 1 0 0 yeah, minus 1, and then we can write into the half of 2 0 0 and plus 0 into 0 0 1. So, this means in this both the cases we can say that we have a non-trivial linear combination, but they are giving us a 0 vector. So, that means this question is affirmative, means we have a non-trivial linear combination of a set of vectors, they can give also is a possibility of a 0 vector into this form. So, thus a non-trivial linear combination may give a 0 vector. Okay, so now we have a like this, there are 3 vectors and take a linear combination of these 2 vectors. I assuming that because we have 2 working is equal to R3, I take any element of alpha 1, alpha 2, alpha 3. So, we take a general, we take write this form linear combination in this form, alpha 1 into this plus alpha 2 into this. If we simplify this, this is equal to this form. So, this may take any linear combination of this form, and this means we can say that this if this is 0 only in the case when this all 3 alphas are is equal to 0. So, this means this is only this linear combination is 0 0 0 only if we have all of them is equal to 0. That means this is a we can write is a trivial linear combination. So, this means we can say that this is only possible this linear combination is equal to 0 vector is only possible when alpha is equal to 0, alpha 1 is 0, alpha 2 0 and alpha 3 is equal to 0. So, that means we can say that simply is equal to this only possibility if we have all 3 alpha is equal to 0. Is this will be 0 vector in only when this is equal to 0. Therefore, this alpha is equal to 0. So, in this case only linear combination that is the gives the 0 vector is the again is a linear trivial linear combination. So, in this case also we have to getting is a trivial linear combination. So, that means we can just define in this means we have 2 types of example. One example we take a elements is, but there is a linear combination is a non-trivial linear combination is giving a 0 vector, but in this case we have to take a vectors which is giving is a only possibility are here the combination is 0 vector only when these are alpha 1, alpha 2, alpha 3 are is equal to 0. That means this linear combination gives the 0 vector only when the linear combination is a trivial linear combination. Now we can define is a linearly independent or linear dependent vectors. So a set of vectors S, we have a v1, v2, vn in a vector space V is called is a linearly independent. When the vectors equation this we can write a linear combinations. So this is no need of this thing. This is wrong. This is we can write in the form of a alpha 1 v1 plus alpha 2 v2 and so on alpha and vn is equal to 0 vector. This is a solution is this means this is the only trivial solution when alpha 1, alpha 2, alpha so on alpha n is equal to 0. So we can say that alpha 1 0 alpha and alpha n is equal to 0. So in this case we can say that this if only possibility is a linear. Yeah, another way we can also say that if we have a vectors S is equal to v1, v2, vn, if the linear combination is a trivial linear combination, we know that prove that the trivial linear combination is 0 vector only when the all the scalars are equal to 0. So this means linear combination is equal to a trivial linear combination also always giving a 0 vector. So here this means this satisfies this equation is trivially. So when we say that a linear combination is a trivial linear combination is called is a linearly independent, or we can say that a set of vectors v1, v2, vn in a vector space V is linearly independent when the vector equation this has a only trivial solution means alpha 1, alpha 2 up to alpha n are 0. If at least one of them alpha is not equal to 0 in this case, this is linear combination is a non-trivial linear combination, and then we can say that the vectors are linearly dependent. If there is also is a non-trivial solutions, then we can say that this is a linearly dependent. Yeah, this is not. Okay. So this is in this case S is called is a linearly dependent. Now that is the question how we check the given set of vectors is linearly independent or linearly dependent. So we have to write in this form. So first we start, we have a set of vectors. We have a v1, v2, vn be the set of vectors in a vector space V. Now to determine whether S is linearly independent or linearly dependent, we have to use the certain steps. First we write these vectors equation in the form of a this is again is wrong, sorry. So we have to just say that we have to write in the form of alpha 1 v1 plus alpha 2 v2 and so on alpha and vn should be we write in this equation for the equation for the variables alpha 1 alpha 2 up to alpha n. Now we have to determine whether the system has a unique solution. If we have to try to solve this system, if the system has a unique solution, or we can just say that if the system has only trivial solution, alpha 1 is equal to 0, alpha 2 is equal to 0, alpha n is equal to 0, then the set S is linearly independent. If the system also have a non-trivial solution, then this S is called as a linearly dependent. If this equation, we can say that this is the equation we have a, if this equation alpha 1 v1 plus alpha 2 v this is alpha 2 v2, this should be this is here, this is not here, this is wrong, this is v2 alpha n vn. So in this case we can say that this alpha 1 v1 plus alpha 2 v2 and so on alpha n vn is equal to 0. We try to solve the system of equation. If the system of equation has a unique and a trivial solution, we can say that these vectors v1, v2, vn are linearly independent. If the system has a non-trivial solution, also has a non-trivial solution, means we have exists at least one of them alpha is not equal to 0, then we can say that the system this S is a linearly dependent. For example, we take a this in R2. So what we have to write first is the equation in the form of a equation 1 into 2 plus we take a alpha 2 and 2 comma 4 is equal to 0 vector. 0 vector in R2 is equal to 0 0. Now we have a this is can be written as a by the R2 is a vector space defined is a component wise addition and component wise scalar. This is alpha 1 comma 2 times of a alpha 1 plus 2 times of a alpha 2 and 4 times of a alpha 2 is equal to we have a 0 0. Now this can be written as a by the addition property alpha 1 plus twice alpha 2 twice alpha 1 plus 4 alpha 2 is equal to 0 comma 0. Now this is can be written as alpha 1 plus alpha 2 is equal to 0, and now we have a 2 alpha 1 plus 4 alpha 2 is again 0. Now we can say that these two lines equations are the parallel, and if it is the parallel, then there is a infinitely many solutions are there. So this means this is otherwise we can say that alpha 1 is nothing but is equal to you have a minus 2 times of a alpha 2. So alpha 1 is depend upon the value of a alpha 2. So this means clearly say that this alpha 1 is equal to minus 2 times of alpha 2. So if we take a alpha 2 is equal to we have a 1, then alpha 1 is equal to you have a minus 2, alpha 2 is equal to we take a half, then alpha 1 is equal to you have a alpha 1 is equal to you have a minus 1. In this way we can set a check. This is a infinitely many solutions. So this means that this clearly alpha 1 is not equal to 0. So this is also exists a non-trivial solution. So this means trivial solution is exist, but also there is exists a non-trivial solution. So this means we can say that this two vectors are linearly dependent. So this is linearly dependent because why linearly dependent? If we take a this minus 2 plus 1, that's why I just say that alpha is equal to minus 2 and then 1, we can get into this is 0 0 vector there. So this linear combination is a non-trivial linear combination, and that's the reason we can say that this set of vectors is a linearly dependent. Okay, now one more example. I take this in R2, and then again we have to write the linear combination of these vector in the form of a this equation 0 plus we take a alpha 2 0 comma 1 plus alpha 3 minus 2 comma 5. Again R2 we have a additive identity 0 0. Now we have to using this property, we can write alpha 1 0 plus alpha we have a 0 comma alpha 2 plus minus 2 alpha 3 and 5 alpha 3 is equal to 0 0, and this can be written as a alpha 1 and minus twice alpha 3, and we have a alpha 2 plus 5 alpha 3 is equal to 0. This means alpha 1 is equal to we can just say that alpha 1 minus twice alpha 3 is equal to 0, and we have a alpha 2 plus 5 alpha 3 is equal to 0. This implies that alpha 1 is equal to minus alpha 1 is equal to 2 times of a alpha 3, and this implies that alpha 2 is equal to minus 5 alpha 3. If we choose alpha 3 is equal to 1, then we have a alpha 1 is equal to 2, alpha 3 is equal to minus 5. So this means this can be written in the form of this form, alpha is equal to 2 1 0 plus you have a alpha 2 is equal to minus 5 0 comma 1, and then plus you have a 1 minus 2 and 1 minus 2 comma 5, and this is giving a 0 0 vector. So this again we have to just check this linear combination is again is a non-trivial linear combination, though this set of vectors is also is a linearly dependent. So this we can say that into this form. Now we have these two vectors. Now this vectors is again we can say that we can write in the form of a independent or dependent. So we can write a alpha 1 0 0 alpha 2 1 2 is equal to 0 comma 0. So this means we can say that this is a 2 alpha 1 is equal to 0, and then we have a sorry, alpha 1 is equal to 0, or alpha 1 is equal to 0, alpha 2 is equal to 0, 2 alpha 2 is equal to 0. This means this clearly again is a, because there is a one vector, this is trivially we can write in the form of a 1 into 0 comma 0 plus whatever this 0 times 1 comma 2 is equal to 0 0. So this means this is 1 is here, we can write this is form of this, because you know that the alpha of 0 is equal to, you have a 0 of a v. So this means 0 of v can be written in this form, is this form. So we write into this form. So this means this can again is this is a linearly dependent, because 1 into 0 is equal to, we have a getting is a 0 0 vector is there. So okay, so now we try another example, and this is clearly we can say that again write in the form of alpha 1 1 comma 0 plus alpha 2 0 comma 1 r2, we take a 0 0. So we have a alpha 1 and comma alpha 2 is equal to, we have a 0 0. This implies that alpha 1 is equal to 0 and alpha 2 is equal to 0. There is only one solution of this differential equation, is only possible 0 0 is there. We have a 0 comma 1 comma 0 plus 0 comma 0 comma 1 is only giving 0, otherwise is not giving 0. This means this linear combination is a trivial linear combinations. We have to alpha 1 is equal to 0, alpha 2 is equal to 0. In this case, we say that this set S is a linearly independent. Okay, now we have to check is this set is linearly independent or dependent. Now this if you take we take is a very simple way, we can say that is equal to, we suppose we have to take a 5 times of a 1 comma minus 5 comma 1 comma 2 plus 1 comma 5 comma 10, and this is giving a 0 0 vector. So this means you can write is a this is combination is again is a non trivial linear combination, because minus 5 and 1 is here. So this is clearly giving the 0 0 vector, and so we can say that this set is again is a linearly dependent set of vectors. Suppose now we take this set of vectors in R3, and again we can say that this set of vectors, this can be only possible solution is equal to 0 1 0 0 plus 0 0 1 0 plus 0 0 1 is equal to 0 0 0. No other way we can get a 0 vector. For example, if we take alpha 1 1 0 0 plus alpha 2 0 1 0 plus alpha 3 0 0 1, and this is equal to 0 0 0 vector, then we can say that this is alpha 1 alpha 2 alpha 3 and 0 0 0, and only possibility is alpha 1 is equal to 0 is equal to alpha 2 is equal to alpha 3. So this means this can, we can say that in this case this subset S of R3 is a linearly independent set. Okay, now we have to check if we have a giving this set of a R3, if this is a linearly independent or dependent. First we have to is checking linearly independent means we have to write the linear combination of this is equal to 0 vector. So we have alpha 1 3 1 minus 1 plus alpha 2 minus 5 minus 2 2 plus alpha 3 2 2 minus 1 is equal to 0 vector 0 0 0. Now we have to just write in this form is we have a 3 alpha 1 minus alpha 1. So this is equal to plus minus 5 alpha 2 minus 2 alpha 2 2 alpha 2 plus we have a 2 alpha 3 2 alpha 3 minus alpha 3 is equal to 0 0, and this can be written as in the form of a, we have to write 3 alpha 1 minus 5 alpha 2 plus ka 2 alpha 3, and then we have a alpha 1 minus 2 alpha 2 plus ka twice alpha 3, and then we have a minus ka alpha 1 plus ka 2 alpha 2 minus ka alpha 3 is equal to 0 0 0. Now we can write in the form of a 3 alpha 1 minus, so this way we can write into this form. So this is clearly. Now in this case we can write this is equal to 0, this is equal to 0, and this is equating these two sets are equal only. This is equal to, we have a 0, this is equal to 0, and now we have a 3 variables and 3 system equations. So most probably we have a solution. So we can write these 3 equations in the homogeneous system of homogeneous equation, 3 alpha 1 minus this and this. Now we have to simplify these two. If we have to just multiply this 2 and then you have a add these two, so you getting simply is equal to, you have a multiplied this is equal to 2. So we have to adding these two vectors. So you have a, you getting the twice alpha 1, and then you have a plus ka, you have a this minus this is equal to twice alpha 2 is equal to 0, and then again we have to take this first one, and this again adding this 2 after multiplication, this we getting into this form is equal to, you have a 3 sorry, this should be equal to, this is equal to 3, this is equal to 3 plus 1, you have a 3 plus 2 is equal to 5 alpha 1, and this is equal to 4, you have a minus ka alpha sorry plus 2 to the 4 minus ka alpha 2, and then multiply 2 is a cancel out, this is equal to 0. So we have a 5 alpha 1 minus alpha 2 is equal to 0, then we have a 3 alpha 1 plus twice alpha 2 is equal to 0. If we multiply it by 2, this is cancel out, then we have a alpha 1 is equal to 0. If alpha 1 is equal to 0, we are substituting here, we getting the alpha 2 is equal to 0. If alpha 1 alpha 2 substitute any one of the equation, we get the alpha 3 is equal to 0. So if we have to simplify these 3 system equations, we get only the possibility solution is alpha 1 is equal to 0, alpha 2 is equal to 0, alpha 3 is equal to 0. That means the linear combination is a linearly independent, and this is a trivial linear combination, and this is a set is a linearly independent. Okay, now we had one more example for polynomials, and we take a polynomials of the real coefficient degree less than equal to 2. So this is all the polynomials in the form of alpha a naught a1x a2x square form. So the polynomial is written in this form. So we take write in the form of this alpha into 1 sorry alpha 1 plus alpha 2 into 1 plus x plus alpha 3 into 1 plus x ka whole square. Okay, so we check is this or not. So this means we can first we have to this 1 plus x ka whole square can be written as a 1 plus we have a 2x plus x square, and the 0 polynomials, you know that the 0 polynomials is always the form of a 0 plus 0x plus 0x square. So this can be written as a 0 plus 0x plus 0x square. So we have a alpha 1 plus we have a alpha 2 times 1 plus x. We have opened this, we have a 1 plus 2x plus x square is equal to, we have a 0 plus 0x plus 0x square, and now this means we can compare the constant. So you have a alpha 1 plus alpha 2 plus alpha 3 is equal to 0. Now coefficient of x, we have a alpha 2 plus twice alpha 3, that is equal to, we have a 0. Now we have a coefficient of a x square is only, we have a alpha 3. So alpha 3 is equal to 0. So this means alpha 3 is equal to 0 gives by this we give alpha 2 is equal to 0, and by these two we can say that implies that alpha 1 is equal to 0. So in this case we can simply say that we said that all these vectors are linearly combination is a trivial linear combination. In this case we can say that these vectors are linearly independent. So that means we can say these vectors are linearly independent. So now just say that this is, we have to So since the polynomials is 0 only if all its coefficients are 0, so we must have satisfy these three equations. So I just observe there. So immediately implies that alpha 1, alpha 2, alpha 3 is equal to 0. So this we show that this is a linear combination, is a trivial linear combination, and then if implies that all alpha 1, alpha 2, alpha 3 are 0. So we may conclude that this 1 plus x, 1 plus x square, 1 plus x whole square is a linearly independent set of vectors. Okay, so now we have to this one more for this. Now we have to check is a set is linear independent or dependent. So now you just take this. We have to first open this x minus 2 ka whole square. This is x square minus ka you have a 4x and plus 4, and then you see this. You can just say that x square minus 4x. So this vector anything. This vector can be written in the form of you have a we can write x square 1 times of x square minus ka 4x, and then you have to write plus 1 by 3 times of 12. So we can write this combination is 1 into this plus this is equal to so this vector can be written as a linear combination of these two vectors. So this means clearly this set of vectors over P2 is a linearly dependent. So this is a linearly dependent. Why? Because this whole square is can be written into a this linear combination of other two vectors. Now what about this? We have to check, and then we again write this is the form of a we have to write alpha 1 plus x, alpha 1 plus alpha 2 x plus x square, alpha 3 1 plus x square, and that means we can write this is nothing but is equal to is a we have a 0 polynomial. So 0 plus 0x plus 0x square. So this means this we can say that the constant term is only here is alpha 1 and alpha 3. So we have alpha 1 plus alpha 3 is equal to 0. X coefficient is here and here. So we can say that alpha 1 plus alpha 2 is equal to 0, and now alpha 2 plus alpha 3 is equal to 0. So that means we have to simplify these three equations. You can easily check alpha 1 plus alpha 3 0, alpha 2 plus alpha 3 is equal to, we subtract this, we can get alpha 1 minus alpha 2 is equal to 0. First and 2 and 3 from 1 and 3 we get this, and now we have alpha 1 plus alpha 2 is equal to 0. This implies that sum of these two is equal to alpha 1 is equal to 0, and then we have a if alpha 1 is equal to 0 from here any one of them this implies that alpha 2 is equal to 0, and this is implies that alpha 3 is equal to 0. So this means we can say that in all of them we can say that this set V is a linearly independent. So this set is a clearly is a linearly independent. So we can just say that this last example for this I will try for a matrix for a whether the set of vectors in M2 by 2 matrix is linearly independent or dependent. Again we write this finite linear combination of these vectors is equal to alpha 1 times we have a 2 1 0 1 plus alpha 2 times we have a 0 2 1 plus alpha 3 times 1 2 0, and now we write a 0 identity is a 0 matrix here in this case. So this can be written as a we have to write the system equation. This is nothing but is equal to we have a alpha twice alpha 1 0 alpha 1 plus 3 alpha 2 0 2 alpha 2, and then we have a alpha 2 and plus we have a alpha 3 2 alpha 3 0 0 is equal to we have a 0 0 0 vector. So we just write this is equal to you have a 2 alpha 1 alpha 1. So we have a 2 alpha 1 alpha 1 0 alpha 1 plus we have a 3 alpha 2 2 alpha 2, we have a alpha 2 2 alpha 2 alpha 2 plus we have a alpha 3 and 2 alpha 3 alpha 3 2 alpha 3 0 0 is equal to we have a 0 0 0 vector. Now, this implies that we have a this plus this plus this. So, we have a 2 alpha 1 plus 3 alpha 2 plus alpha 3 is equal to 0 vector, and now alpha 1, and then this implies that second one is alpha 1, alpha 1 0 0 0 alpha 1 is equal to 0. Now, if we have a, now from this we have a twice alpha 2 plus twice alpha 3 is equal to 0. Now, we have a, by this we have a alpha 1 plus alpha 2 is equal to 0. Now, we have a alpha 1 is equal to 0. From this we get a alpha 2 is equal to 0. If alpha 2 is equal to 0, from this we get a alpha 3 is equal to 0, means we can just write in the form of this is equal to 0 alpha, we have a matrix can be written in the form of 0 2 1 0 1 plus 0 times you have a 3 2 0 1 plus you have a 0 times you have a we have a 1 2 0 0, and this is giving a 0 0 0 is a trivial linear combination in this case. So, this means we have to just say that this set of vectors are linearly independent. So, we can just say that I have to stop today's class here, and in the next class we also discuss some examples and some more example, and some possible we have to discuss some result of the linear independent and dependent. Thank you very much.